And hello everyone and welcome into yet another live stream, and today we'll have some fat rod in the background. There we go, pretty neat. Today we'll be doing circuits, obviously, once again, as always, because I'm still preparing everything for the circuit stuff. And because of that, there we go. Because of that, we'll be doing circuits again. Now, I'm pretty certain this is the same book. My PC kinda crashed and died because that book closed, but I'm pretty certain this is the one. And last time, I'm pretty certain we also finished parallel resistive circuits because we did game when it comes to Kirchhoff law. We have been there. Summary. Series parallel resistive circuits, these will be the difficult ones, right? I think. Yeah, series parallel basically means combining everything we've done. Simplifying series parallel, does it mean combining these two into 200, for example? So for example, this one would be series, so you can combine, exactly, you can combine this. Over here you can show, there we go, okay, I can see the game. I can see the gaming. Determine, okay, you already got our first equation problem thing. Resistive ladder network, so like this, right? This is the same paint, by the way, for some reason. Paint is still fine. It still has... No, paint isn't fine, never mind. This is something that I was calculating for something else. So, over here, you have stuff, right? Now, this... At this point, this is just series. This is just series, so this should be 13k over here. So, okay, so I'm pretty certain, I hope. 3k. Oh, I think I see a way to do it. So this is 13k now. Right, this one is, my goodness, this one is 8k, this right here is 8k, this is 1.5, this is 1.2. Now we can treat this as, now we can treat these two as being parallel, which would basically mean it's, you know, the usual, 1 divided by 1/8 k plus 1/13 k. Which wouldn't give us, oh, this is a prime number. Great, no, it's great, we just have to multiply by 8, that's the only way to do it. 1 divided by, oh boy. One divided, no wait, 8 times 13. 104. Plus 8 104ths. 1 divided by 8 plus 13, which would be equal to 21. 21 104ths, which would be equal to just 104 21st. There we go. So we have 104 21st over on this resistor, which means that if we draw that again, right? Can I just simplify it even more? But just adding points instead. So we'll have this, 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 this. Over here we'll have 104 21st. K. Yeah. Yes. Then 1.2, 1.53, 1.2k, 1.5k, and 3k. Now this is series, so over here it would mean 1.2 times 21 times 21. Which means over here we'd have 1040, 210 plus 252, 210, which would give us how much exactly? Will give us 1292 210ths. There we go. Okay, obviously. Now that we have this, we can do parallel 1.5 and this thing. So 1.5 times 210 would be equal to 114. Oh, I totally forgot to message people about this live stream. How's the audio, by the way? Test 1 to 3. Decent, alright. I'm just doing usual checks I didn't do on the beginning of the live stream. I knew I forgot about something, alright. Checkups, this MKT charity streams. I'm starting a new job today. Because obviously I'm not making money with you. So I'm starting a new one today, and I'm a bit nervous. Today I have kind of an interview for it. Anyway, we're doing this. Okay, so this was combined. Now we have to do the parallel with this. Alright, on it. Which means 1.5 times 210, which means we have 315 210ths. And this is our second, so we will have 1 divided by 315 210ths plus 1 divided by 1292 210ths. And because it's just division hell right now, we can just flip it, so it will be 210 315ths plus 210 1290. This two. Oh, this is such a mess. Alright, let's just do it space up. So over here on this one we'll have 3 5 7. Those are the primes on this one. Now on this one we have 1292. On this one we have 2 and we have 323. Is it 323 is not a prime, is it? I surely do hope it's not a prime. Is it a prime? Wait. Prime numbers list. Prime number, I don't care. I don't care what it is, I know what it is. Prime numbers up to... Oh, this is beautiful! Look at that! How beautiful that is. 323 is not a prime. Great. So now, what is it divisible by? What can you... $323, what can we divide? What can we use to divide 323? That's a good question. 17 and 19. Wow! That is quite a number. So we have to multiply this side. They have nothing in common. We have to multiply this side by 315 and this side by 1292. Great. Cause we'll be back one day. We'll be back one day. I'm really used to speeding to the song. It's a great song. 210 times 315. Oh, then I missed that. Oops, that's... Alright, fine, then 210 times 1292. 271,320. Great. Now 1292 times... Shut it! I don't care. Times 315. 406,980. 406,980. Now we take 66,150 plus 271,320. We get 33,470 divided by 406,980. 1 divided by 3, and now we just can finish this by 406,980 divided by 337,470, and this is the kilo ohms. That's the exact number of ohms that resistor has. Which one were we even calculating this time? We're calculating these two. Okay, so great. Now all we have to do is add 3 kilo ohms to it. So this 406,980 divided by 337,470 plus 3 kilo ohms. Okay, great. What now? Well, Bitcoin, Litecoin, and Dogecoin. These are and there's a French version for this. All right. Wait. Trial division. It just... That's such a cool website. Such a cool website. Alright. Well, we are doing something else today. And so, where were we? More science. Hi, Detecta. Hi. Hi there. Hi. I feel like we should fire up dogs, because I'm grandly outmatched here. So, let's write down what we've got so far. Let's write down where we ended up. And we ended up in 406,980 divided by 337,470. I'm certain that they meant to calculate this with this much precision, right? That's surely what they meant. That surely has to be what they meant. Plus 3. And all of this is k ohms. Now, this is just very simple to calculate because it's just this times 3. There we go, and we get over here we get fraction like this, and it's a number, which is good. There we go. Now we just need to add to this number 406,980, and then what we get is there we go, we get this. Now let's divide this by 337,470, and we get around plus minus, alright, around, so it should be something around this much kilo ohms, like around that point. Okay, let's see. 42k. Yeah. Yeah, I calculated it with a bit more precision. Yes, well, yeah. I feel like more precision might not be too bad here. So I feel like I should. There we go. Give me a second. I'll just do one thing really quickly. Just need a second for it. Alright, and I am back now. Oh boy. So yeah, that one is done. I feel like we understand things in series in parallel. Okay, this is the same thing. This is the exact. I am not going through that hell again, unless someone, then I might. But for now, I don't know if I want to go through that hell again. Because it's not actually. Wait, all of these numbers are relatively easy. Alright, you know what? Let's calculate it with precision. I'm sorry, my second screen is an absolute mess right now. So there we go. So let's calculate it with a bit more precision. There we go. First of all, this at the end is just in series, right? This at the end is just in series, which means over here. Oh, we can actually write down the entire equation all at once. Yeah, I suppose. Yeah, I suppose we could do that. We could, I suppose. There we go. Let's do it. It's a great idea, and listen, it would be a nice, simple, short equation. Okay, it would be just a nice and simple, short equation, made to be very simple, very nice. Actually, this might not fit. There we go. It will be very nice and simple, short equation. So fraction. This and this is in series, which means 5k plus. There we go. 5k plus, and this and these will be in parallel, which means it will be 1 divided by fraction 120 plus fraction and 1 divided by and now we go on, which means this would be 10 plus, and once again this will be this and this in parallel, which basically means fraction 1 divided by fraction 1 divided by 12 plus, and over here we have 2 plus, because this and this will be in series, and then we have 8 and the end, which will be in parallel, which will mean 1/8 plus did I do that right? I feel like I did that right so far. Yeah, it seems right. Okay, 2, 2 plus, so 2 plus, oh, that's where I screwed up, there we go. Over here it should be 1/8, and plus 1 divided by 4 plus 6. There we go, and that hopefully should be the entire equation, explaining this entire circuit. I'm pretty certain, at least. Fraction, no fraction, fraction, no fraction, fraction. Yeah, it should be. Okay, great. Now what we have to do is just solve this equation, and then we will find, well, the answer to our question of how much resistance does this circuit have. So, let's do it step by step, very simple. Over here we'll have a 10. 10 is obviously 2 times 5, and 8 is 2 times 2 times 2, which basically means that we need to multiply 8 by 5, and we need to multiply 10 by 1 by 2 additional 2's, which means by 4. So over here we will get 40 times, this times 4, so 4. This will be times 5, and this will be times 5, which basically is 40 again. There we go. Now that we're finished with this, we can copy, paste. Over here we can remove one of those, and this would be equal to 9, obviously. Now, because of how division works, we can just take that, we can keep 9 over here, and we can add 40 over here. There we go. Now, in order to do this addition, all we have to do is just a fraction, and this will be 2, let's just use 9 over here, and this will be 2 9s, so 18. Now we carry on, we can just add these two together because it's very simple, and 18 plus 40 will be equal to 58. Obviously very simple stuff. Now if we take this, we carry on, then what we have to do is we have 1 divided by 58 divided by 9, which means that by simple rules of division, we can just keep the 58 over here, and we can put 9 on top. There we go. Now if we carry on, we just have to find the same thing for 12 and 58. Now unfortunately 12 times 5 is equal to 60, which would be very convenient, but this is not 60, which means we have to find what they both divide into. So first let's start with 12. 12 is equal to 2 times 2 times 3, that's what 12 is equal to, and 58 is equal to 2, which will give us 25 plus 4, which would give us 29, and I'm pretty certain 29 is a prime number, so that would mean 229. Let me just check the prime number list. Is 29 a prime number? 29 is indeed a prime number, so that means that's all it divides into, which basically means that we need to multiply this by 6 and this by 29. For that, I will right away use my calculator, because this is already too much, and we will get 58 times 6, which will give us 348. Great, that's pretty grand, which means we can go like this, and we'll get 348. 9 times 6 will give us obviously 54. Yes. 12 times 58 would give us 348. 348, and this is times, no wait, times 29 obviously, and so now over here we have to multiply this by 29, and there we go, that should work just fine. Now if we carry on, we can just add together 29 plus 54, which would give us 83, and there we go, 83 over here, and just like so. Now because it's 1 divided by 83 divided by 348, we can take this, we can keep the 83 here and just put the 348 on top. Great, very grand. Now because we have 10 over here, we can replace the fraction of 83 down the bottom and 830 down up the top, because it's 10 times 83. Now all we have to do is we can just add these two together, which would obviously mean 830 plus 348, which would give us 1178, just like so. Very simple indeed. Like so, this. Now because we have 1 divided by this, we can keep the 1178 on the bottom and put 83 on top, just like so. Now we have to find the common, now we have to once again turn them to primes, so we have 20, which is obviously equal to 2 times 5, and 1178. 1178 would be equal to what? Well, 1178 divided by 2, so it will give us a 2, then 589, which, does it divide into 3? 500, okay, 1178 divided by 2, divided by 3, no it doesn't, 589, is it a prime? Don't tell me it's a prime, that would be very suboptimal if that was a prime. 580 what? 89, it is not a prime, very convenient indeed. Now, let's divide it into, well, 5 obviously won't work, 7 also doesn't work, 589, let's divide it into 11, nope, 589, let's divide into 13, 589 into 17, no, 589 divided into 29, no, 589 divided into 19, 31, there we go. It obviously divides into 19 and 31. Very simple primes indeed, as we can see over here. Yes, great. So now all we have to do is carry on and just multiply the 20 by 19 and 31, and multiply the 1178 by 10. Very simple 10 actually, 10 is very convenient here. So we multiply this by 10, very easy indeed, and we multiply this side by 19 times 31, which is 589. 589 times 20, which would give us, obviously the same thing, I'm an idiot, obviously it would give us the same thing, there we go, and now over here we end up with 589, which we then, 589, which we then add together with 830, in order to get 1419. There we go. We get 1419 out of this, and because it's 1 divided by this, we can flip that around. Very simple indeed. It's just 1419, put this on the top. There we go. Now all we have to do is take this, multiply it by 5 in order to get 7095. So this would be a fraction of 1419, and also over here 7095. Now all we have to do together is just add this to 11780, and we get 18875, which, if we put over here on top, this is the exact number of kilo ohms that this circuit has. See, it's very simple. Okay. Alright. I'm pretty certain this most certainly does not divide nicely, but we'll still divide it just to check around what. 13.3, so plus minus 13.3. So yeah, so it should be somewhere around this kilo ohms. There we go. Great. Great. This is the thing. Now let's check if it's correct. 13.3. 13.3, approximately 13.3. You mean 18,875 divided by 1,419. It glimpses into your mind. Palace working that equation out. My mind is more of a mind shed, honestly. It's just I really cramp stuff in there. That was a surprisingly fun equation. And that's what I meant, by the way. That's what I meant when I said that in physics, the most important bit is transforming physical things into equations. Because over here, yeah, this was a lot, but it wasn't hard. Every single step was easy. It was just addition and division. Actually, no division, I just used multiplication. But the actual well, not tough bit, but the actual important bit is this equation, because that, you know, starts everything, and this is the equation that describes this circuit right here. As you can see, it's very schematic, I would say. You can see that we have 1 divided by fraction, 1 divided by integer, 1 divided by fraction, 1 divided by integer, 1 divided by fraction, 1 divided by integer, and there's a reason why this is so schematic. It's because over here we have series, parallel, series, parallel, series, parallel, series. That's why these oscillate like that. All right, so what now? That was fun. The next thing, series parallel analysis. Recognizing those sub-circuits. Yeah, I've gotten pretty decent at those at this point. So we have this circuit right here. 6 volts, 250. Determine the voltage of B. So voltage on this resistor. That's actually a very simple thing to do if I'm not mistaken. If I am mistaken, then I won't be able to do it, but if I'm not mistaken, that's pretty good. Because then it's actually a very simple thing to do. All you have to do is first of all find the resistance of the entire circuit. So resistance would be equal to what? Well, these two are in parallel, which basically means we use our old equation. 1 divided by fraction, 1 divided by 1, k, obviously, this is k, and obviously, and 1 divided by 3k, plus, because this is in series, 250. And now, actually I feel like I should just copy this. I love Fatrat's music, it's wonderful. We just multiply this one by 3, we get 3k. And because of that we get 4. I don't know why I'm thinking so hard about this, it's not hard. And because of that we can just put 4 over here and 3k over here. Now, hiding in blue, if I'm not mistaken, that's the name of the song, it's wonderful. And over here I'm pretty certain it should be 1000 divided by 4, because we just multiply it by 4. And because of that we get, it's 1k actually. And this gives us 4k divided by 4, which is, well, that's gonna be 1k ohms. That's what it is. So that's the resistance of the entire circuit, which means right now, in order to calculate the current, set equal to voltage divided by resistance, right? Voltage divided by resistance, that's Ohm's law. And then we set equal to, first of all, voltage is 6 volts, and resistance is 1 kilo ohm. And which means it would be 3/500ths. I feel like, yeah, it's 6 milliamperes. I shouldn't bother. 6 milliamperes. That's the current. And now, in order to calculate the current going through the voltage on this resistor, what we have to do is we have to do voltage B. I can't find B on my keyboard. Voltage B will be equal to I divided by the resistance of our resistor, which means it will be equal to, hopefully, 6 milliamperes. Oh no, multiplied. I mean, oh, that could have been a goof. There we go. Which means it is actually 6. Yeah, something didn't seem right, because then it would get micro volts, which seemed off. Times the resistance is 3 kilo ohms, which means the result is a kilo and milli cancels out, which means 6 times 3, which is 18 volts. Fuck! It's not, is it? Wait. Voltage B. Ah. Oh, and this voltage B means this entire thing. because that would be different. That would be very much different, because then that would be 1 kilo. Wait, a voltage across B, so this voltage? Nah, listen, mate. Listen, I would love to do an entire stream just to with discombobulate on repeat in the background, but listen, my motto is if you're dumb enough, then everything is a mystery, and because of that, because of that, everything is a puzzle for me. No, this is hiding in the blue. I'm such an idiot. Obviously, this is hiding in the blue. Oh. How could have I gotten this wrong? Right. The song is hiding in the blue. Fat Rats. One of the newer ones. Very good one. I'm pretty certain it was the first of the well, right now not new, but the newer album that was released. First of the series. Anyway, now. Series parallel. Okay, so this is in parallel. I just used the wrong equation. The resistance is correct. Amperage is correct. It's 3/4. 3/4 kilo ohm. Which means 18/4. 18/4 of volt, which would be equal 18 divided by 4, which is 4.5. There we go. Yeah, I don't know why these are a thing, these current drops and stuffs, because they don't help. Must be 6 milliamps. Yeah, this doesn't matter. Alright, next one. Demin voltage B. Okay, if we do if we do this one on the first try, that means I don't think we should go all the way to the end, because it would be just more of the same, and we already understand the rules for it. So, whoops, this thing here, this, we already understand the rules, so there's no point in repeating. Alright, find the voltage B. B would be for this resistor only, but these are in series, so the voltage should be the same. Alright, so on the right we have 3 kilo ohms. Now the entire circuit, okay, the entire circuit's resistance is a bit of a formality, because it's just fraction 1 divided by fraction 1 3k plus 1 3k, which obviously would be equal to fraction 1 divided by which means it's 1/2 of the 1 resistor, something we realized previously, which means 1.5 kilo ohms. Now, that's the resistance of the entire circuit, which basically means that the current of the circuit will be I is equal to fraction 30 divided by 1.5, which is, oh wait, 1,500, very important difference. And I will still use a calculator for this, I don't trust myself with these sort of things, which is equal to 20 milliamps. So now the resistance of this should be voltage of B should be equal to 20 milliamperes times 3 times 3k, which is equal to 60 volts. I think. $60 or $40 or $20. $21k. I wouldn't have guessed. Oh, it's the other equation because it's for voltage. And because of that, we have to check our resistance in comparison to the resistance of the entire circuit. And the resistance of the entire circuit is equal to 1.5 kilo. Wait a second. 1.5 kilo ohms. Yeah, 20 milliamperes. That's correct. And now this current should split evenly down to vertical paths. Good choice, because it tells us that 30 volts. Why would you calculate current then? Doesn't matter then. You're not using that. And also, these are in parallel. As they each present 3 kilo ohms of resistance, 10 amperes each achieves 30 volts for VA. I suppose I can see it, but it's really non-intuitive. Really quite. I would really like to get to capacitors. So I haven't gotten there. Two pairs connected elements. Alright. 10 BC. Wait, B. It's like from B to C. Will it be negative? No. Wait, from B to C. Now you're losing me. What? Okay, this is 3, this is 7 kilo ohms. On the left you have 3, on the right we have 7. These are in parallel, so it would be... So if we were to calculate the resistance of the entire circuit, we would get... one third plus 1/7. Both are primes, so we just have to multiply them. Which should give us 10. That's the resistance of the entire circuit. It's 2.1 kilo ohms. Now determine voltage BC. Well, the current of the entire thing would be equal to 12 divided by 2100, which does not divide nicely. I'll do it 6 divided by 1050, which would be 3 divided by 525. Okay. That's the current doing the entire thing. A bit over 6 milliamps. A bit under 6 milliamps. Now it doesn't divide evenly between two, does it? It probably does not. Divides comprise this respectively. Ordinary resistance, these voltages would also be a fixed value. Alright, so I mean I get it. If the resistance on both sides are equal, then there will be no voltage difference between these two. But they are not equal in this case. Wait, should it be voltage C minus voltage B? Wait, is it something like this? Because then that would be calculatable. Over here we have 1k out of 2, which basically means it's the source is 12 volts. But will it divide evenly? It shouldn't. Well, it shouldn't divide evenly. But if it were to divide evenly, which is a great start already, then the voltage of the circuit divided by right? I'm lost. This equation also is I mean, these aren't equal. Does you mean these? I am so lost right now. So very much hard lost. I knew the parallel series circuits would be harder, but I wasn't expecting to measure in the middle of the circuit like this. How to calculate BNC? Well, because here's the thing. The issue that I'm mostly having right now. We still have it to be the same. Well, technically, yeah, but not in this case, because normally, if I have a circuit, where's my paint? Here's my paint. Normally when you have a circuit like this, right? If we have a circuit that looks like this, and we have a resistor over here, over here, over here, and over here, then we can just add these two together, and add these two together, and have a much simpler circuit, which just looks like this. And in this case, these two are in parallel, which means we can use our 1 divided by 1 divided resistor first, plus 1 divided resistor 2 rule, and also combine them together into a single resistor. And then we have just a circuit of a single resistor. The problem is, in our case, we are measuring over here and over here, which means we cannot combine them, which means we are stuck with 4 separate resistors, which is rather upsetting for this. Because, okay, let's risk it for the biscuit, because then that would mean... So the resistance of the entire equation is equal to 221 kilo ohms, right? I think. I'm pretty certain. I'm not sure actually. So 2100, like this, much easier, without kilo, obviously. And our resistor is 1 over here in this case, minus 12 times once again, oh, but it's divided into 2, which means this should be 3000, I think. I don't know, I think so. I think, pretty certain. Also, it doesn't really make much sense for me that this is at the bottom, but at the same time, I don't know, that's what this book told me, so I'll trust them for now. Then if it doesn't make sense, then I will stop trusting. So this one should be... Wait, what if the current would divide unevenly? And to the left they will go 3/10, to the right they will go 7/10. I'm trying to do it logically, I shouldn't, I really should not, I should just use the rules I know. So on the right that would be 7000. I should just use the rule book. 3000 plus this. And I should just calculate that. So, this would be, let's remove the ohm sign, it's just messy. We all know that these are ohms. 4000, so 3/4. And over here, we have 7/10. Which is equal to 2 times 2 is 2 times 5, which means we have to multiply left side by, which means over here we have to multiply this by 5, gives us 20 and 15, and we have to multiply this by 2, which gives us 20 and 14, and if we get the 12 out of it, like so, because it's unnecessary. Like this. Warbringer? Is it? Wait, actually, I'm genuinely curious. Is it Warbringer? It's Warbringer, yes! That's correct. There we go. Alright. Getting sick a bit. Sorry. Very sorry for that. So, this. This would give us 1/20th times 12, which is just equal to 20ths, which is a very simple thing, because it's just 0.6. So it should be 0.6. It's not. It's so very much not. They divide. Okay, so perhaps the most real is to treat each half as a voltage divider and then subtract VC from VB. Okay, I was correct about this. I was correct about that, even though I was guessing, but I was correct. Good. So VB in this case would be the second resistor divided by second resistor plus first one. Okay, so the second resistor, so like this, let's correct our mistakes. And over here, if we are doing this the same way, then this should be 4, like this. Alright, let's try it again. Which would then mean 2/3 minus 4/7. Over here we use this exact same trick. This is the day we fight. In this case it would be 2 over here, which would be equal to 12 times 12, 144 if I'm not mistaken. No wait, 24 over here, because there should be a 2. 24, 21st, and now we can just check. 24 divided by 21 is equal to 1.1, which is so very wrong. So very wrong. Oh, because of VC. 1.14. Never mind, I was correct. 1.14. That's good. That's good. 1.142. 8, 5, 7, 1, 4, 2, 8, 57, 14. 2, 8, 57, 1, 4, 2, 8, 57, 1, 4. 2, 8, 57, 1, 4, and so on and so forth. Alright, cool. 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 This is tough. But I do know now voltage divider equation. Okay, this is summary. I would like to get to capacitors if I may. Superposition. What is it doing here? Serial analysis broadens our ability to analyze circuits beyond simple series and parallel networks and leverage the laws and techniques and chapters. Yup, it's cool indeed. More realistic model for constant voltage and constant current sources. The ideal voltage source produces a stated potential forever, and not regard to what it's connected to. So realistic model is the battery plus resistor. Given a 0 ohm internal resistance, bacteria in your source. In case of Laplace supply, the internal resistance typically will be a small fraction of an ohm. Alright. The ideal internal resistance of a current source is infinite ohms. That's cool. Determine the current source equivalent for the source in figure. Alright, without reading anything of the above, I think logically it's doable. Because it's actually a very simple thing. If you use Ohm's law, right? Current source equivalent. Okay, I'm pretty certain this is doable using Ohm's law. So volts is equal to I times R, like this, and because of that, we can see that. I know I'm doing it so slow actually. Let's just go straight to the point. I is equal to 15 divided by 50, which would mean 3/10, 0.3 of 300 milliamperes. Now, if this is 300 milliamperes, then would it be just resistance is equal to what? Wait, resistance equal to voltage divided by current, right? So then 15 yes, okay, so 15,000 divided by 300 should give us the resistance, which should give us should give us 50 ohms. I just completed the circle of that's okay, never mind. Yeah, that was it. Retrospectively, that is idiotic. Original voltage source, we can use Ohm's law, which I tried to use and I failed miserably. Oh no, it is 50. Oh. Never mind them. You should always be identical. That was that was fun. just let a rule that they are always the same. That was splendid. All right. Voltage B for the circuit. This. Do I have to? Oh, this looks like pain. Like, this doesn't look hard. It looks annoying. boy. This looks like massive pain. Nope, we are not doing that. Superposition theorem, because that sounds fun. Multi-source series second can be only be applied to networks that are linear and bilateral. Further, it cannot be find values for non-linear functions. All right. So we basically won't combine the sources, we'll do something else. So, okay. I like this method. I really like this method. So the basic idea is, if I understand this correctly, is to compute this for each source and then subtract in the end. That's actually very nice. All right. Let's try this. Oh, that's the same thing. All right. It's fine. It's fine. We can do it. So let's compute the thing. First of all, we'll have to find the equation. We'll have to find two equations actually, for first and second. So here's the basic idea. We'll have I of the first source on the left source and I of the second source, which will be the right source. Now, this is equal to fraction voltage divided by the resistance, voltage of the first source and resistance from the first source's point of view, and this would be the same thing except for the second. And then the actual I would be equal to I1 minus A2 minus I2. There we go. So, first of all, the resistance of this is just series, and this is in parallel, these two. Which means this would be equal to fraction of 15 volts, 1 plus fraction 1 divided by fraction 1/5. K, I should add K's over here so that I won't forget later on. Plus 1/4 K. And that's for the first one. For the second one, we have 6 volts. And over here, we have 4K plus, and we have 5 and 1. Alright, step by step. Over here, this will be 20. This will be 920K. Alright, so then this is equal to 1K, it will be 9K9, so this will be 29K. And considering that this is just 1 and 15 times, then that means this is equal to 29K. 9 times 15 is what? It is at least 7 times 15, 135. 135, there we go, which is equal to, well, divided by 29,000. It's tiny, that's the point, there we go. 135 divided by this, it's small, that's the entire idea. Now for this thing, which should be easier. Over here we just do it 5 and we get 5, and because of that we end up with a 6. And now we turn this around, we get 6, and this should be 5K. And this one should be fraction and 6 times 4, which is 12, 24K. In the end we end up with 29, and we do the same thing, which means 6 times this, which means we get 29K, and over here 6, which means 36. There we go. Now, for this thing, we end up with 29,000 in both cases, which is convenient. Some might even call it too convenient. It seems off, but fine. $135, which basically means 99 if I'm not mistaken. 99. So 99 divided by 29,000 is equal to around 3. So it should be something like 3 milliamperes. Wait, we're looking for voltage. Well, if we are looking for voltage, then it certainly is different. That certainly is a different story, because I'm pretty certain 3 milliamperes would not be an answer to voltage. So we have B. I'm pretty certain it should be times 20k nines, which would leave us with 20k thirds, well 20 thirds, which would be equal to 20 divided by 3, 6 volts. This is 6 volts, but it's a different thing, it's this 6 volts. across. Wait, what? No. Oh, so voltage is across them, and then what? Because this is B for the from this point of view. Am I wrong? Well, in this case, well, if I use the 3 milliamperes, which I got from the calculation using the fancier method, which I no idea why it exists actually. Now I'm thinking about this. So what's the answer actually? The voltage simply add. Those two voltages simply add. But why they add if one is going the polarity is from plus to minus, top to bottom for V, so like this. So this is hell. Oh boy, there are so many rules, so many different rules, so many unnecessary different rules here. Okay, and another theorem, damn it. Any single point linear network can be reduced to a simple voltage source, series with internal resistance. Which means this the problem with this book, it has a lot of stuff in it. The problem is it's very school university like, very college university like book, which means it doesn't actually tell you why the things are true or why are they useful. It's just it tells you stuff. Section, yeah. Pretty dense too. It's not that's the problem. It's not dense. It's very much not dense. If it was dense, I would be fine with that. I love dense books because in dense books you can read one page and you have, you know, knowledge of the stars in your brain. But this is very much not dense. Straight. Like, for example, this process turns out to be quite straightforward in this particular circuit due to the open no current flows through. This is very much this sentence is just thrown in here because there is absolutely no need for this sentence. That's why it's very much, it's not dense. It's just it just lacks the, you know, examples, the real examples that people actually care about, the real step by step. Over here we have first over here second, third, fourth, combination, this resistance as noted earlier, neutral circuit, device. Yup, and it's still up to this point. Doesn't tell you why it is useful. Like cutting the circuit, yeah, I get that, but why would we cut the circuit? What's the difference between you working with this circuit? Like, this circuit seems more complex, if anything. Why would we convert this into this? Oh boy, alright. I'm drinking coffee today, I'm trying to detox again. It's driving me mad. An example is shown in figure 641. Only two connections exist to the remainder of the circuit. Maybe a single component or large multi-component sub-circuit. Cool. As there are many ways to construct it, there are impossible 7 equivalents. No current due to the open, no current flows through R3. Okay. Thus no voltage develop across R3, and therefore ETH must be equal to the voltage developed across R2. But but why and therefore? If there's no voltage, if there's no current developed across R3, which makes sense, right? It's connected to nothing. It's cut. Then what does R2 and ETF have to do with anything? Why are they connected? I mean, I guess they are connected over here. That makes sense. But apart from that. Second part is finding the hidden resistance. Okay, so we treat this as the only voltage source, and because of that, this is in series, that's why we add it, and these two are in parallel, right? Because it just, diverge like this. So these two are in parallel, and because of that, over here we have this, that they are in parallel. Source drive, remember everything is done from the vantage point of the cut or port, so from this, yes. Equivalents are not limited to single source circuits. Wait, so that's it? That's the end with this? What did we achieve? Find equivalent of a network with several sources. Finding the open circuit output voltage with the requires something to work. For example, superposition of source conversions. Finding the resistance to unchanged. Remember to replace every source with its ideal internal resistance for a simplified network. As noted earlier, the original circuit could be cut in a number of different ways. I still, up to this point, don't get why this would be useful. I cannot, I just don't, I don't know what we did. Like we made up a value, we calculated the value, and that's it. I don't get what we did here. What? We did nothing. What did we achieve? We basically replaced did we just replace resistance with voltage? That's pretty cool, but why? Yeah, that's what we did. We replaced a resistor with a voltage source. What? Why? Why? I don't... It's also great use when determining the maximum power transfer, like in this chapter, is the long way home, in this example, as the advantage of being more efficient, several different laws are being considered. Determine the upper voltage. So it's more efficient. In order to do it, all we have to do is just... What happened with this high one? Why is this 100 here too? That's also... So many questions. Just... Oh, because this one... I swear, I just... Understand the thing, I don't get why it exists. That's my only thing. Because it seems like we are doing the exact same thing that we would be doing, except this time we cut the circuit. Alright. So over here, this is a very complex circuit, right? There's parallel, series, voltage sources, current sources, it's the whole thing. And what are we doing here? We are trying to find the E. We're trying to cut this part out, or the left side? We're trying to cut the left side out. And in order to cut it out, what we have to do is Wait, I don't know this one. Which one is it? Oh, it's hunger. Okay, yeah. Never mind. Okay, so after we show this one, so no resistance, open this one. Yes, these two are in parallel. And because of that, we over here, we have... Because of that, we have fraction 1 divided by fraction 1 1k plus fraction 1 3k. And over here, we just multiply both these by 3 and we get 4/3 k, which means we get 4 and 3k. That's the resistance of this side. These are in series, which basically means plus this. Now these two are in parallel, which basically means that, oh boy, let's first divide 3000 by 4, 750, which means we get 2k ohms, which means fraction 1 divided by 1 2k plus fraction 1 divided by 6k, which then leads us to get 6 and 3 over here, which leads us to get 4 in general, which leads us to get 6/4, which means it gives us 1500 ohms. 1500 ohms as the resistance of the entire left part, which means is this what RTF is equal to? Then I suppose, except we don't have RTF here. Determining the RTF is not the final result is 1.5, yes, kilo, yes. It's a little bit more involved. One possible. Wait, so can I just replace this left part with RTF? Oh, I have to replace it with ETF and RTF. Let's use a source conversion. Okay, so in our case, in order to find ETF, what we have to do is voltage is equal to I is equal to volts divided by, so 1 milliampere, 10 milliamperes. That's this source. Then we have this source going up with this one. Which should give us 25 milliamperes, and then multiplied by this resistance, I think, which would be multiplied by 3000 plus 1 divided by, oh no, I'm sorry, multiplied by 1 divided by fraction 1 to 3, like this, plus 7250s. Which I suppose we should probably, there's only one way to do it, honestly. First of all, we can just run this by 10, so 300 and 725. This we can take 5 away from it, which would leave us with 60. Over here, once again, we can take 5. which would leave us with 12, 2, which would leave us with 6, 2, which would leave us with 3 and 3. So these are 5, 5, 2, 2, 3. On the other hand, 725 divided by 5 would give us 145, so we have 5, 145, another 5, which would give us 29, and 29, so 5, 5, 29. So we have to multiply this side by 29, so 3000 times 29, which is 87,000. Gives us 29, and the right side by 12. There we go. Is monkeys next? Am I mistaken? No, I'll do the rain. Okay. So over here we'd have 39 plus 2, 41, which would give us 41, 87,123. This, and because of that, put 0.25 times 87,123, and we get this divided by 41, which will be a, yeah, and it will be wrong, by the way. I feel like, I don't think this would be 53 volts. I don't think it would be equal to 50. Yes, 14. What? So current across the 6K. That's how you. That's how you are calculating this. Current across 6K. But what? Yeah. Results in total 25 milliamperes feeding upwards. Yes, with 1 ohms in parallel to 3 kilo ohms. Or 750 ohms. So you count this and this in parallel. We can use the current divider rule to determine the current flowing through. It makes so little sense here. I just give up. I just I don't like it. Another theorem, obviously. We don't have enough theorems. I feel like we need a couple more. To a single current source with parallel internal resistance. Okay, yeah, so it's a Thevenin's theorem, except we have current and no, not voltage. So resistance is the same, that's at least neat, cool. Resistance simple. Resistance, you just have to calculate the maximum power transfer theorem. Oh, we don't have enough theorems. We need more. Assumable the resistance. A useful question to ask is, what value of load resistance will yield the maximum amount of power in the load? You know what? I ask myself that every day. Well, it is not true that maximizing load power is a goal of all circuit designs. It is a goal of a portion of them, and thus worth a closer look. Consider the basic circuit depicted in figure 6.6.1 with source E and internal resistance Ri and load resistance R. Alright. I would like to describe the load power in terms of load resistance. The ratio may normalize the voltage source E to 1 volt and the source resistance to 1 ohm. Yeah, convenient. Indeed, R becomes a normalized value, that is, it no longer represents a simple resistance value, but represents a ratio in comparison to R. Yes, E will equal scale the power of both Ri and R, so precise value is not needed, and thus we may as well just 1 volt for convenience. Yep, so 1 divided by R. 1 divided by 1 plus R, yes. Load power is so that means if we normalize our voltage and if we normalize our internal resistance, then we get this equation. The only question that I would love to ask is what happens if we don't normalize. Oh, there it is, the monkeys, yeah, okay. Unless this is only for graphing purposes. I feel like we are going into a bit too much detail before capacitors. I just wanted to understand the basic components, and it's just like, this part is kind of cool. It is, but the only issue is that you have to understand all of these graphs are normalized, for normalized voltage and resistance. And whilst voltage is something that I would relatively understand how it can be normalized, the fact that we have 2 different values that are normalized, it's a bit of a pickle. Because if we don't normalize them, one aspect is it to make me see on how to address the circuit. Yeah, but the thing is, so far I'm pretty certain we've learned 8 different theorems about 3 different components. So you know, it's like, I'm not saying it's ever slightly bit of an overkill, but it might be a bit of an overkill. Because so far, up to this point, we are working with only 3 components, may I mention. Potentiometer is just resistor, so that still counts as a resistor. Only 3. We have the voltage, the source, the current source, and the resistor. If you are trying to optimize some values for a circuit, you might try to design. Yeah, but that would be handy. But right now, did you think? Oh, okay. Here's the thing. Let's take these 2 equations, right? We have I squared R. That's power. Okay, let me just actually do it like this. The 2 battery source circuits. Yeah, they are very similar, and they are, I would even call them practically the same thing. And you know, whilst it is really neat, I don't think I will be cutting the circuit to determine the resistance of the Thevenin resistance, the Thevenin voltage, and the N-guy current of all of them, because I feel like I would be just working with the entire circuit. It seems a bit simpler. I squared R, which is equal to resistance, right? So now we will have like this. This is what it looks like when it's not normalized. Internal resistance plus the resistance times the resistance. There we go. That's what it is when it's not normalized. Which means if we expand even further, there we go. Over here we ask it, okay. There we go, plus 2 plus squared times R, which would be then equal to this. And this is how a not normalized version looks like. Like, this is the not normalized version. We can see how it turns to the normalized version if we set the internal resistance to 1 and voltage to 1. It does turn, right? Yes, it changes, but this is the not normalized version. Why was I even talking about that actually? It's a good question. So 3 segments on horizontal lineup plus 1. Courses art. Eventually how to get that straighted, yeah. How and what now? What do you want? Resistance equal to 1, this is easy to see with the completed power curve. Let's look at the horizontal axis. Desmos. I'm tired of this. E is equal, let's do E is equal to 10, because why not? Let's do resistance is equal to 10, because why not? Let's do resistance, let's do internal resistance with capital I, which is, oh, this I, 10. Internal resistance, because that'll be simpler. Now let's grab them all. We have E, we have R. There we go, neat. Have resistance. Actually, this is not that important. We have resistance, then we have this. Internal. There we go. Internal. Now the next one will be internal squared. Oh, they used X for the resistance, didn't they? That actually makes sense. Wait, didn't I? My this was. What just happened? That was terrifying. I lost my train of thoughts. What was I talking about? I mean, Normalization, yes. The ratio of the resistance of what is what matters. So load power as a percentage of the maximum. So you get the maximum load power when the resistances are equal. Is equal to the internal resistance of the driving source. Cool. Great. Delta Y Okay. I feel like I'm 5 years old, I'm learning all the shapes. Component configuration such as the previous networks cannot be reduced to a single resistance using basic series power conversion technique. One method for simplification involves converting sections into more convenient forms. Are 3-point networks containing 3 resistors. Due to the manner in which they are drawn, they are referred as delta networks and Y networks. Yeah, I can see it. These configurations are shown in figures 871. In this particular case, the delta version is run upside down so that the terminal designations match those of Y configuration. Yeah, I was about to say, so yeah, makes sense why they would draw delta this way. Understandable. So redrawn, also called as pi networks and T networks. I can see T, I can't really see pi, I guess, but no, delta, it's delta. Delta sounds cooler. True equivalent circuit would present the same resistance between any 2 terminals as the original circuit. So, so XY, the resistance XY is equal to A parallel to this plus this. So these two in series and this part. Okay, makes sense. That makes sense. Kind of. If you like close, yeah, actually does make sense. It's actually very simple. Back one day. This is a song by the Father Back One Day. So okay, delta one. The delta one is actually very. Which one is paint? There we go. Delta one is actually unbelievably simple because when you have delta, right? When you have delta, then you have a resistor over here, over here, over here. So if you want to calculate from this point to this point, then you can also redraw that as a square, which, as we all know, is simpler, like this. And then we can see that these two are in parallel, and we can redraw that even further because you know, might be actually even more convenient. And we can see that they are in fact in parallel. Yeah, these are all the same. So yeah, that makes sense. We have parallel to this series. Yes, I understand that. How about this Y? Because Y looks way more complex. Delta Y conversion, okay. Assuming we have the delta and we are looking for the Y equivalent, no, I would normally go the other way. Note that we have 3 equations with 3 unknowns. Oh, you're trying to convert the resistance. Wait, isn't Y just straight up more complex? Because this is just a parallel series. That is a very simple circuit. Deep C. Okay, if that's how you're counting this, then I suppose it actually could be a bit more convenient. And this is just math. This is just straight up math. Like, I can do it on stream. It might be funny. It might be funny to do it. But this is just pure math. Like, we won't use us because that will be too annoying. But we will use A, B, C, D, E, F. So 1 divided by A plus 1 divided by B plus C is equal to D plus E. Let me just... These are just 3 equations. This actually looks extremely fun. D and F and E and F. This is BAC. And this is the CBA. We'll be back one day. Alright. This looks quite pleasant. It is certainly it looks quite pleasant. Because we have 3 different equations and 3 different constants, which means we can calculate them. The only issue is calculating. So, let's first assume that none of these resistances are equal to 0. Because I feel like that's a solid thing to assume. That's a pretty solid thing to assume, that none of these have 0 resistance. Because in order for them to have 0 resistance, they would either have to have 0 resistivity, which is unrealistic, or 0 length, in which case, what are we even talking about? So, if they have 0, then that's really convenient because we can divide both sides. And they also don't have infinity, that I should probably also mention that. And this is really convenient, we can divide both sides however we want. So, we can simplify the first equation. This I'm about to have some fun because this is. Then if we multiply both sides by this, then on the left we'll get a 1, and on the right we'll get this. Preferably I would love to end up with, wait, actually goal. That's a good question. What goal? First let's try with D. So first we have the equation for D. Very simple equation indeed. So we have our equation, we're trying to create 3 equations for 3 different things. First of all we have the D equation, which looks like this. Very simple. Now let's try to create the E equation, which cannot be described in terms of D. So we cannot just subtract D because that would be too easy. We could, I suppose, do this, but I feel like this probably will lead to some problems. Because right now we would have to describe F in terms of D minus E. And E could be described as minus F, yeah, that's the issue. So we probably should describe E in some other way. Oh, maybe we shouldn't. Wait, let me try it this way first. Because that actually might just work. Kind of, almost. We can describe E as equal to this, and now the only thing left to do is to describe F. F will be a pain because we kind of half-assed our way through the entire thing, which means that right now when we have to describe F, it will be painful because, well, let's do it this way. Plus this, that will be equal to 2F plus a D plus E. There we go. Plus 2F. Now, D is equal to this. Minus E plus E, we can cancel this, lovely. And because of that, we can take this, we can do minus this, and this is nothing to be found over there. Great, we have 2. This is going to be fun. So, I feel like I did something wrong, but Okay, certainly, first of all, this the fact that all of these are to the negative first power cannot be good for me. It just cannot be good for me. I mean, in theory, we might be done. That is actually a solid. That is actually kind of solved equation technically. It's not simplified, but it certainly is solved. Like that, yeah. That's equal to f. So like, if we use these 3 equations, we can calculate every single value here. it's a very, not gonna lie, it's done a very dumb way, because this is f then, right? And this is e, which means this is like so. There we go. Make it approved, equation solved. If... There we go. Now, if we know the values for A, B, and C, and we do, we can find value for any single one of those. But I feel like they have a bit of a better way, don't they? Yeah. How would you look at that? It's actually pretty similar to what I did. Yeah, they just went over the simplifying bit, just like I did, so it's fine. Suggestion. Can you go out? Yeah. Okay, so that I am not memorizing that. No, I am not memorizing that. I refuse. That's... No, I am not memorizing that. I refuse to memorize that. That's such a pointless thing to memorize. I mean, it doesn't matter how useful it is. There are too many things to memorize, and it's too easy to do it logically. I refuse to memorize this. Y delta conversion, that's the probably more important one. B, C, D, E, and B is this. This is so unbelievable. I'm sorry, but this is just... This is so advanced when it comes to resistance and resistors and everything. It's so unnecessarily advanced. I just want to get capacitors. That's it. Null immersion analysis dependent sources. I swear. Circuits from figure 7 to begin labeling connection nodes and assigning current directions. Interested in current junctions, that's places are split. Second green figure. The current directions are chosen arbitrarily and may be the opposite of reality. The wrong direction will ultimately show up reversed, but the computed node voltage will be just fine. Okay. So the one node is chosen as reference. This is the node to which all other node voltages will be measured against. Typically, the reference node is ground, although it does not have to be. Well, seven chapters later, they mentioned that. 7 chapters later. It's fine. We now write a current summation equation for each summing node, except for the reference node. In this circuit, there's only one node where currents combine, or the ground, and that's node B. Points A and C are places where the components connect, but they are not summing nodes, so we can ignore them for now. Using KCL on node B, we can say that current 1 plus current 2 is equal to current 3. Okay. Next, we describe these currents in terms of the node voltages and associated components via Ohm's law. For example, I3 is the node B voltage divided by resistor 3, whilst I1 is the voltage across resistor 1 divided by resistor 1. This is VA minus VB, therefore. I feel like you skipped over a couple of parts. So what you do over here is you take this E1 so this is the same equation, right? Voltage B divided by voltage 3, yes. Voltage C minus voltage B. Voltage A minus voltage B. Yes, I think. Okay, makes sense. Noting that not working LaTeX and not working LaTeX, with a little algebra, this can be reduced to a series of products of consistent voltages. Yes, we have 1 divided by first resistor of first thing. Great. Sick. And because of that, if we divide this entire side by this, we get the voltage on B. Consider a more direct approach is possible. Consider the circuit of figure 7.2.2, which looks way more complex than the previous one. We start as before identifying nodes and labeling currents. This is shown in figure 7.2.3. I cannot even read numbers now. We then write summation equations at each node except for ground. We consider currents entering a node as positive and exiting as negative. Like right now, I feel like a fucking expert on resistors, which would be great if not for the fact that that is the simplest. It's the simplest component in existence. There isn't a single component that could be more simple than the resistor. I want to get to capacitors. Capacitors are the one that I don't understand. Right now we are learning how to solve some really specific problems for some really advanced circuits, but we don't know how to do anything with capacitors. 10 millions, yeah, I know, just do algebra and then you'll figure out. Determine the voltage B in the circuit. Okay, let's try this. Let's try this, cause why not? Voltage B in the circuit of figure 7. Yeah, cool. So we have this. I'm pretty sure we had the exact same example a couple of times before. We're doing it over and over again. It's just every single time we have more tools. So over here we have the first current plus second current is equal to first current, which means that we have E1, E2, voltage of A, that would be E1 divided by, no, the voltage would be, first of all, for that we would need to find the current, and then from current have to find the so we have, now to find the current, we need voltage of A minus voltage of B divided by 1k resistor plus this, which is the voltage of C minus voltage of B divided by 4k resistor, which would be equal to voltage of B divided by the 5k resistor. Great, now okay, so this is our equation. We have to find voltage B in this. That's what we are looking for, right? First of all, let's find voltage A, which would be, I'm decently certain, based on E1, we can calculate voltage A by using, well, by finding the resistance, right? And then we will have to do over here parallel 1 divided by 1/4 k and plus 1/5 k, which would give us 1 divided by 520 plus 4, which would give us 920k, which would give us 20k divided by 9, and this plus 1, which would give us plus 1k plus 1k, which would give us 29,000. 29k divided by 9. There we go. This is the resistance, which means in order to find the current, the I1, this will be equal to E1, which means 15 volts divided by the 29k, which would be equal to what? Well, it would obviously be equal to 15 divided by 29,000, which is not a lot. Or we can just, do 15 divided by 29, and this would be just half a milliampere, 0.5, so half a milliampere. Apparently, does it feel right? It doesn't, but who am I to say what's right and what's wrong? 5, so 1/5 plus 1/5, so that would mean 6/5, so that would mean 5/6. 5/6 plus 20, 5/6 plus 24, so that would be 29/6. Oh, over here it should be times 9, so it should be 4.5. Oh, almost screwed up there. And it should be half a milliampere. Half a milliampere times 6, which means 3 milliamperes. There we go. And now voltage across the A, which will be equal times 1k, which will be 4.5 volts, and voltage across C, which will be equal to 3 times 4, which is 12 volts. 4.5 and 12 volts. Those are the voltages. Now 4.5 and 12, so 4. Okay, so now we can finish the equation. We'll get 4.5 minus VB divided by 1k plus 12 minus VB divided by 4k is equal to 5 VB divided by 5k. And now all we have to do is solve it. So in order to solve it, we'll just let's expand our bullet a little. There we go. Now in order to solve it, all we have to do is just figure out what to do with the VB. So we can always First of all, multiply both sides by 5k, which means 5k times. And over here, this one, and multiply both sides by 4k too, which would mean, yes, this. And over here, 4 times 4.5 minus VB plus 12 minus VB, which is equal to VB times 4k I suppose we could divide both sides by 4k actually, so we'll have 5/4 times 16, okay, calculator, 4.5 times 4, which would be 18, 18 minus 4 VB plus 12 minus VB, which would be equal to VB. And now we will get over here 5/4 times 30 minus 5 VB, which is equal to VB. And now if we multiply, all you have to do is multiply this by 5 and divide it by 4. And this would be great. Or we can multiply both sides by 4 actually. I take it back. Yeah, we can multiply both sides by 4. Then we get 5, which will be 150. 150 minus 25 VB, which is equal to 4 VB. And then what we can do is we can move this to the other side. So we get 150 is equal to 29 VB. And now because of that, we can just divide it by 29. So 150 divided by 29 is just equal to very simple 5.172 volts. That's what VB is equal to. 5.172 volts. Higher, it's higher than 6 volts. So it's flowing from. VB is actually equal to 11 because why not? I mean, honestly, there is S over here. What unit is this? There is. What unit is this? Alright, take number 2. What are the units, by the way, over here? I mean, what are the given? E? Where's the E? E is obviously 15.6. So I shouldn't. So VA is equal to E1, and VC is equal to E2 for the first time in the entire book. It's K. It's fine. And because of that, VA, so we'll get, which is equal to 15 and 6. 15 and 6. Not a problem. It's just, you know, 15 minus VB. Can I just call it B? It would be simpler. Divided by 1k, 1000, plus 6 minus B divided by 4000 is equal to B divided by 5000. Now if we multiply both sides by 1000, what we get is a simpler equation. 15 minus B plus 6/4 minus B/4 is equal to B/5, And now if we multiply both sides by 20, we get an even simpler equation. We get 300 minus b, 300 minus 20b, plus 30 minus 5b is equal to, just expand the board a bit more, 300 minus 20b, so multiply both, yeah, so 4b, that's what it's equal to. And now because of that we get 330 minus 25b is equal to 4b, so 330 is equal to 29b. And now if we take the calculator and we go through this, divided by 29, we get 11.379, which is perfect. Cool. Can we get the capacitors, please? I swear. Cool. So mesh analysis. So you can mesh. So voltage equals L1 plus voltage equals L3. Voltage equals R2 plus voltage equals R3. Cool. Great. Oh, over here we have to do the delta thingamajig, and I know. I refuse. It's enough. Dependent sources. Dependent source is a current or voltage source whose value is not fixed, but rather which depends on some other circuit current or voltage. The general form for the value of a dependent source is y is equal to kx, where x and y are currents and or voltages, and k is the proportionality factor. For example, the value of a dependent voltage source may be a function of a current, so instead of the source being equal to, say, 10 volts, it could be equal to 20 times the current passing through a particular resistor, or V equals 20I. Oh, we could just do capacitors, or we could just, you know, this is, I may be wrong, I feel like this is a much more complex thing than I feel like this is a much more complex component than capacitors. 100 LX, so 100 times this. I feel like this is a much more complex component than the capacitors. For goodness sake, this is a differential equation. I mean, kind of. That would be a differential equation. This is okay. Okay, I suppose the rate of change of it is independent, but no, the rate changes very much, and this is not a differential equation. I swear. Why? We are in chapter 7. We're in chapter 7. And this still hasn't been the same. Okay, it's fine, make it. Just do the circuit. And then everything will be handy dandy. Alright. There we go. Let's do the circuit, lads and gents and ladies and gentlemen. Let's do the circuit. So, we have a circuit here, which is very lovely. So, we have a circuit, which I will just screenshot actually, because I am not drawing that. That is I have no idea where it was. Oh, it was pasted on the very beginning. Makes sense. Alright, cool. So, we have a circuit. Very lovely circuit. Very, very fun. Very friendly, lovely circuit. Over here, this is 100 LX, which means that... Wait, but is it current voltage? What's the... Current of... Oh, it's current. Right? This CCCS would be typical of a simple model of a bipolar junction transistor. Oh, it's a transistor! Oh, cool! We are doing the inside of a transistor. Alright, so here's the thing. I'm guessing it's current because, you know, that's normally how current sources look like. So here's the thing. We have our lovely voltage source over here. It's very fun. It's fun. It's very fun. I like it. It's great. And now this voltage source goes through the 10k resistor, which means that on the point A, what is the current? Well, it's current, if you might remember, it's equal to voltage divided by resistance, which means 1, which means it would be 1 divided by 10,000, which means it would be 1/10 of a milliampere over here. And considering right now that this is 100 times, right, this, then this source would give us 10 milliamperes. That's the source. Now we are trying to find VB, so voltage over here, and we are also trying to find VC, so voltage over here. Now if this gives us 10 milliamperes, right, then we have no parallel stuff or anything. I'll just ignore this entire thing for now and hope that will work out. So, oh, but this comes back over here and it's fine. So, here's the thing. Let's start the resistance. We can shorten this entire part. Oh wait, we cannot. We cannot shorten this entire part. This is a this is a voltage divider. Isn't it? I feel like it is. I feel like it is indeed. So 2/17, right? I is equal to, but now if we divide both sides by, no wait, now if we divide both sides by I, then we get 1 is equal to I, and if we divide both sides, so 1 divided by E is equal to 2/17 I. Great. And now 1 divided by E is equal to 2/17 I. So now if we if we just you know, if we just don't give up for a second, hypothetically, and then we could decide that over here we would get voltage. Can I just try to do it a simple way for now? So without this dividing or anything, just because then VB, actually wait, VB should be simple. 2/17, no, 2/17 is for this, right? Or maybe for this, wait. 1 divided by E is equal to 2/17 I. And if I over here is equal to how many? 10 milliamperes. That means 1 divided by E, which is the inverse voltage. It's very, it's very, you know, it's a very basic unit, inverse voltage. It's, you know. Then 217 times 0.01 would give us the inverse voltage. Now, if we then voltage would be equal to 1 divided by 2/17 by 2 instead of 17. I feel like this is wow, this is so wrong. This is so wrong already. So I messed up bad here. Oh no, 17. No, that's correct. I think 1/100. So this would be 1/100, which means it will be 2 1000. Don't think I make it. Oh, there's make it. Okay. Now here's the thing. I is equal to 0.01, which is equal to E times 2/17. If we divide both sides by 2/17, then we get 0.01 times 17 seconds, which is equal to E. Sorry, to voltage, by the way, because I'm completely doing the wrong thing here. Voltage of B, I think. I hope. OBS overlay warrior something different. It's not a difference. I think it's made. No, I don't think it's a differential equation. I'm pretty certain there's no time. So there's no time. So it's not okay. Now this times this 17/12 divided by 100 basically. So 70 seconds actually divided by 100, which means we get 85 millivolts, which I don't think is correct, honestly. If you were to ask me, I don't. Oh, because to K makes even less sense. Oh, because it's K and K over. No, wait, that actually does nothing for me. Well, let's just do it the simple way, which means 2. So let's do how many millivolts this has? This has 10 millivolts, right? So 20 volts VB. If I were to just guess, just honest god guess, that would be 20 volts. And over here, it should be divided in some way, shape or form, but let's just say it actually should be divided. Wait. Wait, should it be 15/17? I have no idea what this is, because on one hand you should just multiply resistance by current, right? And that would give you a voltage. The problem is it makes no sense, because from what I've learned in this book is that this should be plus minus, which means voltage should drop over here, which means it would make no sense for it to be 17 times 10 milliamperes. That would give us 170 volts, which is wrong. It should drop. So in order for it to drop, we could calculate using the 15/17, right? E is equal to I. Then we would get is, in order to get the E, we'd have to divide by this, which means E would be then equal to I times 17/15. And thus will be 10 milliamperes times this, which seems even worse because we would get millivolts. Doesn't seem right. Maybe too big of a drop, but on the other hand, it's 15 kilo ohms, so maybe maybe it's just a drop. 1.3 times 10, 11.3 millivolts. That seems so off. Seems like too big of a drop. At the same time, it is divided. What's this? So we could use this, I suppose. So all the currents. Oh, because current is also going in from the left. Oh. 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 Okay. So now when it comes to this, we have current going in and this. So this is going this way, right? And this is going this way. Those are our lovely, lovely currents. So current over here would be equal to 101 L. So, okay, current exiting onto this resistor would be equal to 101 LX. Or IX, actually. IX, I suppose. I think that's IX. IX times 2K would give us the voltage VB. There we go. Now over here it should be just, that should give us the voltage VB, but I'm certain it won't give us voltage VB. There is something else going on here, something way more weird probably. Okay, so I mean, if we were using Ohm's Ohm's law, then this should be the out current, which is 101 IX times 2K, unless it's not 2K, unless it is. Oh wait, oh no, wait, it's equal to VB divided by 2K, which means if we multiply both sides by 2K, then we get this. Yes, that's the equation, yes. Which then would mean that why do you have VB here? Why don't you just multiply, like this is 101. Why do you have VB here? Wait, what? You can just solve it to this, and then will the IX where did you get this VB from? I mean, if that's the equation, you multiply both sides by 2 kilo ohms, right? Then you get this right here. And then in order to figure that out, we'll have to get the Ix. Oh, because Ix is equal to 1 wait, what? Ix, so this is equal to 1 volt minus VB. 1 volt from the battery. Why minus VB? I mean, 1 volt divided by 10, I understand that, but... Oh, minus VB because different in... Obviously, yes, okay, makes sense. So we have 101. Actually, we have 202,000 times 1 minus VB divided by 10,000 is equal to VB. And then in order to solve it, we just first of all cancel 3, 4, 1, 2, 3. Okay, so this will be divided by 10 still. And because of that, we get 220. No, wait, 202. 1 minus VB divided by 10 is equal to VB. So if we multiply both sides by 10, then we get 202 minus 202 VBs is equal to 10 VB, which means 202 is equal to 212 VB, which means 202 divided by 212 is equal to 0.95 volts over there. So 0.95 volts. There we go. They also did the milliamps in the meantime. I don't think it was not necessary. Now, so now next one is VC. Now for VC, boy, VC actually. Yeah, this negative is there. And we just get 100 Ix here because electricity is magic, and this division just perfectly divides 1 this way and 100 this way. Yeah, but this is the simple thing, right? Yeah, this is the simple thing, okay. Summary. Yeah, okay. Capacitor! That'll be it for this lesson because, oh my goodness, it's been 3 hours. Okay, we got that, it's fine, we got that, okay, cool, fun, alright, so, we got there in the meantime, in the end we got there. It just took us 3 hours to get from understanding resistors to really understanding resistors. How many chapters does this book have actually? I'm curious right now. How many chapters? That's 10. Like a marathon, yeah. I mean, so here's the thing. Fundamentals. So physics, resistors, capacitors, inductors, magnetic circuits. Cool. No, that's great. It's resistors are important, apparently. Who would have thought? Alright, that'll be it. I have to go. I have a job interview today, for which I'm very, very not excited. So, for now, that'll be it. Thank you everyone so much for watching, and have a great day. Bye!